Chapter 8, Section 2. Well, we've looked at graphing, and really graphing for systems is a good way to get a visualization of what a solution looks like in the different scenarios and so on. Well, we need a little more accurate way to get those solutions. And the first one we're going to look at is substitution method. And this is an algebraic, they call non-graphical methods of solving systems are often superior to graphing, especially when we get fractional ordered pairs. And this is a case here. So this example, they've actually drawn a picture of that. And notice that the intersection, or this point where these two lines cross, which would be the solution to this system, because it's an ordered pair that's a solution for both equations, is fractional. It's really hard to pick out exactly the values for the x and y there. So we're going to find a different way in here. The first one we're going to look at is substitution. And it's nice the way these are set up because I can go, hey, it's already solved for x. So if I took what x is equal to, which is this y plus 1, and I put it into the other equation and substitute it in for this x value, I'll end up with an equation with one variable. And if I have one variable, I can solve that and figure out what that variable should be equal to. And then when I know that, I can find the rest of the ordered pair. Because then I can put a number back in for y, basically use substitution again, and find out what the x value would be. So that's what they're doing here. And they start numbering these equations just to keep them as a reference point because it's easy to confuse which one you're working with. So here's our system. X plus y equals 4 and x equals y plus 2. Equation 2, this one right here, says that x and y plus 1 are the same number. In other words, they're equal to each other. So we can substitute in the y plus 1 for the x in equation 1, this one right here. And that's what they do. So they take equation 1, they put this y plus 1 in for x here. That's what's in parentheses, really a replacement for this variable. Hey, I got a new equation with one variable, and then I solve that. They go through the steps kind of in a weird way of subtraction and division. But they solve it in y equals 3 over 2. Well, there's a fractional y value, or fractional height of this ordered pair, which is 3/2. Well, to find out what the other one then is, I can take this equation, which is handy if it's already solved for x, and put in 3/2 in for y, and you get 3/2 plus 1, which is 3/2 plus 2/2, or then you can add the numerators, and get 5/2. So the solution to this system is the ordered pair 5/2, 3/2. Remember to keep your order of your ordered pair ordered, right? It's kind of a lot of ordered in there. Okay. So let's see if it truly is a solution to the system. Well, I need to take these ordered pairs, put them into the equation, see if it makes it true. Well, it makes this one true, and it also makes this one true. So it is a system solution. Okay? And it's exact. It's not some guess off what I'm looking on a graph paper. Well, let's look at example 2. This is solve the system using substitution again. Well, I need to get one of these equations equal to a variable. And probably the easiest one to do, you could use either one, but this is the easiest to solve for y. And that's what they do, is they add a negative 2x to both sides, and you get y equals 6 plus negative 2x. Okay? Well, that's equal to y. So I can go into the other equation here, and where the y is, I can put in this 6 minus 2x. And that's what they're doing right here. I need to distribute that multiplication. I get 3x plus 24 minus 8x equals 4. And then they solve this equation, and they get x equals 4. Well, now I have a value for x, and I can substitute again. I can go back to any one of these variables, these equations, put in a value of 4 for x, and then solve for y. And they end up with this ordered pair of 4, negative 2, which then you can see, hey, does this ordered pair work? This is a visualization of example 2 is that these lines intersect. I'm looking for a common or one ordered pair that works for both, which would be the system solution. Well, this one, they show a visualization of this, and you say, hey, I got an issue here. They don't intersect, right? We went through this in section 1. This is a system that there is no solution. There's no points, no ordered pairs that will make both of these equations true at the same time. So, if you think about what we know about graphing, and these are in the slope-intercept form, I should be able to look at this. Hey, they have the same slope of -3. That means that they're parallel or lay right on top of each other. Well, they have different y-intercepts, so they must be parallel. And what does that mean? It means that there is no solution. You could stop right there and say, hey, there's no solution to this system, I'm done. But if you don't catch it thinking about what you know about parallel lines, you may start using the substitution method, and which is okay. You start doing this, and these are both equal to y, so I could make these two equal to each other, and that's what they did, is they took this -3x plus -2 and they substituted in for y right here, and you end up with this equation with one variable. And you start solving that. Well, I need to get the variables on one side. I add the additive inverse of -3x, which is 3x. If I add that to both sides, here I get 0, but I also get 0 here, and I end up with -2 equals 5. No variables left, and this is not true. There's no way I can make this true, or pretend that it's true, or wonder if it'll be true ever, because there's no variable in there. Really, it's just saying -2 equals 5. This is not true. Well, when this occurs, if you miss this graphically, or the idea of it graphically, when this occurs that I get into basically something that will never be true, that means there is no solution. In other words, these linear equations are parallel to each other. I'm going to stop there and do another video and basically go into the elimination method just to break it up.